Hello. So today we're going to be looking at applications of the supremum and infimum of sets on the real number line. So in order to do that, I'm going to first recall these fundamental definitions. So definition. So let S be a set which is bounded above. Okay. The supremum of S. So then U is equal to the supremum of that set S if U satisfies the following properties. One, U is an upper bound for S. Two, if B is an upper bound for S. Then U is less than or equal to B. So this is the definition that we take the supremum of a set S. And likewise, the infimum is the analogous definition for lower bounds, right? So these will be the fundamental definitions that we use in today's lecture. So hopefully, if you understand the supremum, then you'll also be able to obviously translate this for lower bounds. So maybe I'll say in words that the supremum is the least upper bound, and the infimum of a set that's bounded below is the greatest lower bound. Okay, so now that we have recalled these lectures from the last lecture, or we've recalled these definitions from the last lecture, we can proceed with today's lecture. And in this lecture, we're going to discuss how the supremum and infimum can be applied to infer fundamental properties of the set of real numbers. And we will begin by showing that supremum and infimum of a set S satisfy algebraic properties such as addition, multiplication, subtraction. So with that in mind, let's start by showing how supremums can interact with set addition. Okay, so let's look at the following claim. So I'll call this claim A. So if S not equal to the empty set is a subset of real numbers, and we'll say the set A plus S is equal to the set of all A plus X, such that X is in S, where A is just some real number. Okay, so S is a non-empty subset of the real numbers, and A plus S is defined to be this set, where A is just some real number. Then we'll say that the supremum of this set here is equal to A plus the supremum of x. So that's my claim. Okay, well, with this claim, we're going to next argue why it's true, give the proof. And we'll start by saying let U equals C best, the supremum best. And under this assumption, so x is at most U for all x and x. Okay, that's just by definition. Hence, or well, maybe not hence, you can say something like, therefore, if we add that real number a to both sides of this inequality, we get x plus a, or I'll say a plus x is at most a plus u for all x in the set S. Okay, so, but what does this imply? This implies that a plus u is a upper bound or an upper bound for that set a plus s. So I'll just go ahead and say that, which implies that a plus u is an upper bound for the set a plus s. So if we're looking now to consider the supremum of that set, the supremum is the least upper bound of that set. So we can infer, so hence, the supremum of the set A plus S is at most this upper bound which we found. So again, our goal is to show that this equation holds, not that equation, this equation here. So the way that we're going to do that is show that this is less than or equal to that, and then that's also greater than or equal to that, which implies inequality. So we're half the way there at this point. Okay. So next, we're going to show that this is greater than or equal to that, and that'll finish the proof. So next, let's say B be an arbitrary upper bound for the set A plus X. Be an arbitrary upper bound for A plus S. Okay. So what does that imply? Also, so we're going to say something like A plus X is at most B all X and X. Since it's an upper bound for the set A plus S, this inequality proves false. So maybe consequently, I shift that over here. Consequently, X is at most B minus A for all X and S. So what that means is that B minus A is an upper bound on this set S. So I'll say that. So consequently, this inequality for all X and S, which implies B minus A is an upper bound for S. Since it's an upper bound for S, the supremum of S is less than or equal to this number here. So we can say hence the supremum of S is at most that upper bound. Okay. So since we've let U be the supremum of S, so maybe and so again, if we add A to both sides of this equation and replace S by U, we get A plus U is at most V. Okay. So since V was an arbitrary upper bound for the set S, we can choose V to be the supremum, not the set S. V was arbitrary upper bound for the set A plus S. So since we chose that arbitrarily, we can just choose V to be the supremum. So we have therefore maybe if V is equal to the supremum of A plus S, we have that A plus U is less than or equal to the supremum of A plus S. So now, observe that the supremum of A plus S is at most A plus U and is at least A plus U. So this implies that they equal. So maybe one last sentence. Hence, A plus the supremum of S, which is equal to A plus U, is equal to the supremum of A plus S. And that finishes the proof of this statement. Now there's a little subtlety here if you're not used to dealing with it. That one way to show that an equality holds is to first show lower bound and upper bound, and if a quantity is bounded above and below by the same number, then they must be equal. So that's how we proved this claim. We first showed that sup A plus S is bounded above by A plus sup S, and then we showed that A plus sup S is at most the supremum of A plus S. If those two things are both true, which they are, then those quantities must equal. Okay. Okay, so let's look at another claim. I'll call this claim B. Okay. If A and B are non-empty, just write it right here. Non-empty subsets of R such that little a is at most little b, A in capital A and little b in capital B, then the supremum of A is at most, I'll write it over here. Then the supremum of A is at most the supremum of B. Okay. All right. So again, we're going to argue why this is true. And whenever I write these proofs, it's important that you follow along, and after lecture, you try to replicate them, like read line by line, right along with what I write down. And then after you follow the logic, then try to piece together the logic on your own without actually looking at what I give you. This will build your intuition as to what your next sentence in your proof should be. Okay, so let's look at the proof here. So for any arbitrary little b and capital B, okay, notice A is at most B for all A in capital A. So since we have the, for any B, we can just pick an A, and any A in A is going to be bounded above by B. We see that any A that we pick is an upper bound for the set A. Okay, which implies, or hence, we can say that the supremum of A is at most B. Okay. And that's for any choice of B in that set capital B. Now, this inequality holds for any choice of B, right? So, okay. Oh, I almost really messed up. I was like, this doesn't make sense. This should be the infimum of B, the greatest lower bound. I apologize for that. Okay, so hence the supremum of A is at most B for any B that we choose. So what that means is that, so we can say something like since sup A is less than or equal to B for all little b and capital B, sup A is a lower bound than the set B. Since the infimum of a set is the greatest lower bound, we know that the infimum must be greater than or equal to sup A. So we can just say that once the supremum of A is less than or equal to the infimum of B. And that establishes that claim. Okay. So let's do another thing. Okay. So next, I suppose that we should move to how supremums and infimums can be applied to functions, and in particular, um, the the range of a function is some set of real numbers as we've defined it. So if it's a set of real numbers, then we should be able to use supremum and infimum to say something about how the ranges of functions behave. So before looking at these applications, I should probably remind you of the definition. So a function f, which maps some set D to R, real numbers, is bounded of if the set f of D, which is just the range, so this is the set of all f of x such that x is in D. So if this set is bounded above. So this is what it means for a function to be bounded above. It's in terms of the range of a function, the image of a function, which is just a set in the real set of real numbers. It should be implied that there's a similar definition for a function to be bounded below, right? If the image or the range of a function on a set is bounded below, then say it's bounded below. And we say that the function is bounded if it is bounded both above and below. So f from D to numbers is bounded if the image f of D is bounded from above and below. So that's what it means for a function to be bounded. Yeah. Okay. So hopefully that definition is clear. So I suppose with the following example, we'll show how to work with supremums and infimums of functions. So here's my plane. I'll call this thing C, I think. So let f and g be bounded real value functions with some common domain D. Okay. Okay, so if f of x is less than or equal to g of x, all x in the common domain D, then the supremum of f of D, so that's the, again, the range of the image of D under F, is at most the supremum of G of D. Okay? So when you look at this, you should, before proving anything, you should kind of reason why this claim should be true. Now, with all the proofs that I write in class, I think about them quite a bit before I write them down for you. So even though it looks like I'm just like claim, proof, claim, proof, claim, proof, that's not how it's actually working. That's just how I'm lecturing. For the notes I make, I write down a claim and then I kind of sit for a little while, like thinking about the problem and trying to figure out why this is true. And you should do the same. Okay, so let's look at the proof. So first, observe that for any choice of x, we have that f of x is at most g of x. And since g of x is bounded, it has a supremum. And this is for all x and d. Okay. So what this means is that the supremum of g is an upper bound for f of d. So hence, sup g on d is an upper bound for f on d, the image of d under f. Since it's an upper bound, the least upper bound of f of d is bounded above by that. So this implies that the supremum of the image of d under f is at most the supremum of the image of d under g. And then we're done. That establishes the desired inequality. Okay. So it is important to notice or observe that this hypothesis here says nothing about the relationship between the supremum of the image of d under f and the infimum of the image of d under g, right? This is only saying that under this hypothesis, the sups of these ranges is related by this bound, but that's not necessarily the case for the infimum of one set versus the supremum of another. So for example, maybe say f of x equals to x squared, say g of x equals to x, and take a common domain to be the set of all x such that, I don't know, 0 is less than or equal to x, which is less than or equal to 1. Okay, so notice now that if we're in that interval, for any choice of x that we pick in that interval, so if x is in B, this implies that f of x is at most g of x, right? If you pick any x in that interval, for example, you pick x to be a half, then f of a half is 1/4, and g of a half is a half. So this bound holds for any x that you pick in that interval. So, so with that observation, just notice now that the supremum of the image of D under F, that's clearly going to be 1. But the infimum for the image of G under D is going to be 0. So under this hypothesis, yes, we can bound the supremum of F by the supremum of G, but we cannot bound it by the supremum by the infimum of G. For example, this is 0, that's 1. So that hypothesis doesn't say anything about the relation in general between supremums and infimums of functions. But with that observation, let's next consider a slightly different version of this claim. And it's a very subtle difference as well. In fact, I'm going to write it here so you can just compare the next claim to the statement here. So, in D, maybe, and these functions f and g are going to satisfy, they're both bounded real value functions with some common domain. The only thing that's going to change in this claim is what I write here. And what changes? It states that if f of x is at most g of y for all x and y in the domain, then we can say that the supremum of f of d is at most the infimum of g on d. Take a moment to look at how this claim seems very similar, but now we're getting supremum is bounded above by the infimum. So here, the supremum isn't bounded above by the infimum, but the hypothesis here is different from the hypothesis there. How is it different? Well, consider this statement here. This is for a fixed x. You fix x, you pick some x, f is no more than g evaluated at that one x, right? Whereas here, if I pick an x, any y that I choose in the domain, any y that I pick, g is bigger than f at that x. So this is a much stronger hypothesis than this. This is for fixed x. This is for x and any y that you pick. So there is a subtle difference in how these claims, the hypothesis of these claims are, which that subtle difference gives us a much stronger upper bound in the supremum of f of g. Whereas here, the best we can say is sup g is an upper bound in the sup f. But here, we get infimum of g is an upper bound on sup f. So this is stronger, but the hypothesis is much more involved. Okay, so let's look at the proof of this. So, so maybe I could say like maybe choose some arbitrary x and d and observe that f of x is at most g of y for any choice of y, for all y in D. Okay? So what does that mean? It means that for that choice of x, f of x is a lower bound on the image of D under G. So maybe we see that again. Since the infimum is the greatest lower bound, this implies f of x is at most the infimum of G on D. Okay? But this inequality holds for any choice of x, right? We just picked x arbitrarily. So since this inequality holds any x in D, that means that the infimum of the image of D under G, that means that that's an upper bound on the image of D under F. So the infimum of G on D is an upper bound for the image of D under F. Since the supremum of F of D is the least upper bound, we have that the supremum is mostly infimum here. So this implies the supremum of F D, since that's the least upper bound, and that is some upper bound, that means that that's less than or equal to that value there. That establishes the claim. Okay. So hopefully you see that there is a difference between this hypothesis and this hypothesis, and that difference implies that under this assumption, we get a much tighter upper bound on the supremum of that. Whereas here, the best you can say is that that upper bound is the supremum. So there is a difference. Okay. Okay. So I'm splitting today's lecture into two parts. The first part we just covered, which was proving these claims, which show how you can use supremum and infimum to we can use them as applications to get interesting results on how sets behave on the real number line. With the next lecture that I record, I'll be talking about what's known as the Archimedean property of the real numbers. So that'll be it for today, or that'll be it for the first part of this two-part lecture.